So now for our last talk of the session. There's always a kind of a name collision when we talk about live programming. There's people who actually work on code, and then there's people who write code live to make music. And now we have an intersection of those coming together where we're going to have a musical talk, but also using program synthesis techniques. So Mark Santolucito, assistant professor at Barnard College at Columbia University, is going to talk to us about exploring human-in-the-loop program synthesis with live coding. And I'm looking for, my ears are looking forward to this talk.
Thank you for the introduction. I hope my ears can live up to your expectations. Right, my name is Mark Santolucito, and I'll be talking about exploring human-in-the-loop program synthesis with live coding. That's quite a mouthful, so the first thing I want to do is just break down this title to figure out a little bit more about what we're talking about here. So I see this as three different components: the human in the loop, the program synthesis, and the live coding. So I want to work from the bottom up here and give a little bit of context for what I mean by live coding. And as Brian said, we have the sort of two different interpretations of what live can mean in this context. We have live programming and live coding. So I'll be talking about live coding here. Live coding, I like to say, is the act where the act of programming becomes a critical part of the end product. So in live coding, we're actually not pursuing software engineering to get to a final state of the code, but the evolution of the code itself is what we're interested in. So Nick Collins, a famous live coder, calls live coding the art of reprogramming, changing your mind about a process once established. And so what this actually looks like, you can see here a little pre-COVID picture from Baby Castles, a performance venue in New York City. Messica Arson's performing live coding, and you can see the artist has their laptop and is coding. The code is on the screen being projected. And live coding is this performative practice where the audience listens to the music that's being produced, or the visuals that are being produced, or whatever media is being produced by the code, as well as watching the evolution of the code. Now, there's a lot of overlap between live programming and live coding. They're not really distinct, and live coding doesn't have a really solid definition anyway. But I like to look at live programming as more of an IDE design principle, where we're saying we want to bridge this gap between our code and our output and our interactions. And live coding is one particular instantiation of that, where we're leveraging live programming. Doesn't necessarily need to be that way, but in most cases, live coding, you can think of live coding as taking place inside of a live programming environment. Okay, and then a little bit about program synthesis. We've sort of been dancing around this idea of program synthesis all day. I'm going to be talking about program synthesis in the sense that given a formal specification, we want to generate code that satisfies that specification. And in this case, the specification could be a logical formula, could be input-output examples. We're all familiar, I'm sure, at this point with flash fill from Excel, the classic input-output example use case. I want to focus specifically on these two directions, SyGuS and in particular CVC4. So in recent years, there's been an amazing amount of progress in the program synthesis domain, especially in standardization and tooling. And I think this is what's really exciting. This is, to me, once tools and processes start to become standardized and have good support in their tool sets, we can do interesting things. So I'll talk about syntax-guided synthesis in a little bit, as well as CVC4, a SMT solver that supports syntax-guided synthesis. And what I'm really looking at is trying to explore how we can leverage general purpose program synthesis tools in live coding and live programming. Okay, so right, general purpose meaning SyGuS. Okay, and now finally, let's just touch on this human in the loop aspect of program synthesis. So human in the loop program synthesis really is just everything that we've been talking about today. But from my perspective, when I look at program synthesis, I see that program synthesis is guessing too much at what the user wants. We provide a specification, and then really we're asking too much of this black box. And so what we want with human-in-the-loop program synthesis is how we allow the user to guide synthesis at the most critical parts of the synthesis algorithm. Now, we've seen this before. Everything today, a lot of the authors of this output-directed programming, direct manipulation interfaces are here in the Zoom room today. So, very cool stuff. The one point I want to make is that prior work has largely been focused on leveraging these code templates and not general purpose synthesis, and looking at the human aspects of human-in-the-loop program synthesis, and not how human-in-the-loop program synthesis actually has an impact on the algorithmic limitations of synthesis. Now, all of this is probably a good thing. We want to be focusing on how users actually use our tools, but there's two sides of the same coin in a way. We can not only benefit the users, but we can actually hopefully gain some insights into how to best structure synthesis by involving our users. So I really like to see this in both directions. And then we also saw there's a lot of challenges in getting general purpose synthesis to work. Code templates are effective in many cases, but how do we push past that? Okay. So before I talk a whole bunch about all sorts of details, I want to hop into a live demo so we can sort of get a sense of what it is that we're going to be working with here. So here I have the tool that I've built for related to this work. This is a drum machine, or a step sequencer. So here we have a block, a matrix of buttons effectively, and we can turn these on and off. And let's see, hopefully you can hear some noise now. And so this drum machine is going to loop, right? So I'm defining a pattern, a rhythmic pattern that's going to loop. And what you'll notice is as I'm clicking on the buttons here, code is already being generated. So we'll get into how this code is being generated in a second, but I just want to demonstrate a little bit of what happens. So here I'm building up my pattern, and you can see code is being synthesized here. And every time we synthesize code, we're going to synthesize code in two different lines, basically a map over an array, and then we're going to splice that array. And I'll get into why we do that in a second. But this is bidirectional, so I can make changes here as well. And now we're getting different code. So I can make any changes I want here. And I get interesting different patterns here. Let's see. And you can fill this with any sort of value. So I'm going to fill this with some code that wouldn't reasonably be synthesized. Okay, and then the other thing I just want to point out is that I have some sliders here that can change the pitch of the drum beats that we hear. Okay, so this is the basic idea behind a drum machine, and as well you can see the code that's being generated and how we could edit that. So let's talk a little bit about what's going on there. Okay, so the code that was being generated was all using as a backend SyGuS, which is syntax-guided synthesis. And syntax-guided synthesis, given a grammar of allowable functions, we want to generate a function that satisfies some constraint. And so we're using satisfiability, modular theories, and SMT solver, CVC4 to solve these problems. And this is really important because by using an SMT solver, which is a separate tool, modular tool to our front end of synthesis, we don't need to keep changing our front end. Every time that SyGuS synthesis gets better in CVC4, synthesis gets better in our tool as well. So this is following the same sort of pattern that we saw in program verification community, where a lot of front-end tools were being built on top of SMT solvers, and those front-end tools just keep getting better every time the solver gets better. We're looking at a similar space here, and the challenge, though, is how do we connect the code, the direct manipulation editor, and the synthesis queries together into what SyGuS expects, which is a space of allowable functions, as well as the constraints. So this is the basic sort of flow of interactions that we have. We initially start with, typically you'll change some notes in your direct manipulation editor, your step sequencer. This is initial synthesis. It will change that code the first time. Then maybe we'll do some manual coding in here. That should then update the direct manipulation editor, and then we can go back around in a circle with program repair when we change more in the direct manipulation editor. So the challenge here is really, how do we move around these three different modes of interaction with the code? So first I'll start about, just talk briefly about how we actually turn these step sequencers into constraints. So this is a bit domain specific, and basically what happens is we have a number of different patterns. The first thing we do is split each track into an independent synthesis problem. We'll just look at the TOM1 pattern right now. And then we generate example constraints based on the time index and the note value. So here we're saying at index 0, we have a 1, at index 1, we have a 0, et cetera, et cetera. And so we generate constraints accordingly in the SyGuS language. And one thing you'll notice is that we need to prune, what we do is prune large subsequences of a common value. So we have a pattern here, and the user just hasn't gotten around to clicking all of these buttons yet. That doesn't mean that the user wants all of these to be 0. It just means they haven't been specified. What we do is we say, okay, let's leave those out of our synthesis request. So as you can see here, we only have the first 5 indices specified in our constraints.
About a minute left, so
okay,
we can wrap up quickly.
Yes. And then we get our function out of that synthesis, and we can then translate that synthesis result into a map over the array. Right. And so this is a high level idea. We're going to split each track, generate the example constraints, prune the synthesis, and then translate the result. Some of the key limitations right here is that each pattern is unrelated to the other patterns. That's something I'd like to be able to figure out. How do you get all of these synthesis requests building off of each other? We're still, although we're using SyGuS for the contents of the map for the actual return value here, we're still somewhat tied to a template in that it is a map over an array. So how do we break away from that? And then finally, this does not scale so well when we run synchronously. So I'll skip over some slides about the issues with running synthesis in parallel. But some of the exciting future to-dos are how we connect this to a hardware drum machine, because I'd really like to have a hardware interface to program synthesis. And there's a number of future questions. So this is all still some preliminary work, but hopefully I can get some great feedback from you guys. And if you're interested, I'll pop the URL here into the Zoom chat. Thank you.
All right, let's thank Mark. That was a lot of fun. My ears enjoyed that.
I'm glad.
Does anyone have any questions for him? Rebecca, it looks like you're up first.
Yeah, thanks, Mark. This was a really cool demo to see. In the demo so far, it seemed like you mostly interacted with the drum dashboard. I'm wondering, I'm not very familiar with the live coding domain, but in live coding, are there scenarios where it would be more intuitive or more expressive or less tedious for people to write to actually make more edits to the code itself rather than interacting with the UI.
Yeah, in live coding performances, typically you're only working with code. You're not working with a UI at all. And so I guess I was mostly editing the interface just because that's the program synthesis side of things. But the coding interface is, it's a coding interface, and you can write anything you want here. It's just JavaScript. So if I were to maybe do a whole live coding performance with this over a period of maybe 10 or 15 minutes, then I probably would want to be doing more editing of the code.
Cool, thanks.
Ravi?
Thanks, Mark. That was a really cool demo, really cool talk. I'm also really interested in particularly how you kind of like embed these code templates in the context of your general purpose language. And, we haven't thought too hard about it yet, but I guess maybe one idea is like if you imagine, like the code template as being the literals in some more general syntax of the language, I wonder if like some kind of tracing or provenance tracking during execution of the program to basically, track the flow of data down to those like literal code templates, and then from there you can use that to kind of seed your constraints. But yeah, in general, like that would be really great to be able to kind of like embed these code templates in a more composable and more flexible way. That'd be really great to make some progress there.
Yeah, that's really a very cool idea to actually think about the code templates as first-class citizens of the language. So the example I've given so far, we just write general purpose JavaScript code. Typically, if you're actually looking at live coding, everybody's using a DSL, right? You don't want to be writing out JavaScript code in a performance, but actually looking at that, and so these DSLs often become sort of languages themselves with a whole their own syntax and semantics. For example, the title programming language for live coding. And actually looking at, say, okay, well, that is sort of a template. If we treat that as a first-class citizen in the semantics, how does that connect to the synthesis? Very cool.
Mary Beth?
Super cool work. I've always found synthesis really intimidating, so this actually encourages me that it's maybe approachable and maybe will work if I actually try it. If I'm understanding correctly, are you going to have a drum that somebody can play and then it generates code?
Yeah, pretty much, yes. So
so
this
cool.
this is a virtual drum machine, but typically these come as hardware. So musicians will have a drum machine box. And so they can type in by turning buttons on and off their drum pattern, but also they can play the drum pattern by smashing the buttons on the drum machine. So what I'd really like to look into next is, and it's actually more of an engineering problem, is how do we actually connect this virtual interface to the physical interface and start to bridge the gap not only between the code and the output, but also the physical interaction of building that code.
And then I think Raleigh will be our last question for the session.
Oh, but you're muted.
Muted again.
We'll get used to this eventually. Yeah, so I had a question about the kind of workflow where so as I understand it, you resynthesize the kind of function, and then you sort of translate that into the map over the array. So am I right in thinking you regenerate that each time?
Yeah.
I guess what I'm wondering is, are there kind of use cases where the user might say, actually, I'm happy with that extension, if you like, to the template that you just generated. I want to keep that part, but now just synthesize some changes to that. So like extending the kind of the vocabulary of literals.
Yeah, this is definitely a top priority. Right now you get a little bit of that in that each drum pattern is treated separately. So when you change one drum pattern, it's not going to impact the synthesis results of the other ones. But it would be interesting to look, okay, well, can we break this up even more fine-grained than that and say, okay, well, you've made some edits, and actually tracking, which lines of code the user has edited, how we, because this quickly devolves into a clippy situation where we're suggesting edits to your code or overwriting code in the middle of a performance, and the performer says, wait, what happened to all of my code? So there's a very tricky dance to play here.
Thanks.
All right, let's thank Mark and all of our speakers once again.